Okay, so in this video, we're going to talk about two-source interference of light. That's section 26.2 in your textbook. And it's based on an experiment that was done back in 1800 by an English scientist by the name of Thomas Young. What he did is he started with a monochromatic light source. I can't tell you exactly what his source of light was. He probably did not have lasers available yet. But there are some sodium lamps and things that, with filters, can be used to get pretty much a monochromatic source of light. So we start with a screen. And he cut a very narrow slit in this screen. And when I say narrow, we're talking maybe 1 micrometer, a millionth of a meter, very narrow slit. And in front of that, he placed a second screen, also with 2 very narrow slits. And they were placed probably, this is really enlarged. So if this was a slits were maybe a micrometer in width, they were placed maybe 2 or 3 or 4 or 5 micrometers apart from each other. Now, one of the things that we probably should have learned in a previous chapter is that when light goes through this aperture, what we see is it spreads out. And it spreads out as if it had circular wave fronts. It's called Huygens principle, but it spreads out. And so when it reaches these 2 slits, which are equally spaced from that, it's going to pass through them, and that light too is going to spread out with circular wavefronts. And this is far from being drawn accurately, but what we're going to see is in between there'll be places where these will add together and places where they will subtract from one another, where we'll get destructive and constructive interference. So what you might expect to find if you put a screen over here, if you did not know anything about physics, you might expect to find 2 bright spots of pink light. But in fact, what you find looks much more like this. In the center, there's the main bright spot where they come in equal distance. And then there's another one, and then another one, another one. And we get these bright bands of light. These bright bands, of course, are because of constructive interference. That those waves that are in phase are adding together at points, and in between, they're of course canceling each other, just like we talked about in section 26.1. Okay, but what he did is he came up with some formulas besides the one we had in the first section to describe what's going on. So I'm going to kind of erase all of this so we can look at a slightly different picture. So back here we've got some monochromatic light source of some case. I'll put something back there. But we've got a screen, or a couple of screens, however, but at some point there's 2 slits very close apart, very close together. Those slits are very, very small. That's greatly exaggerated. And down here, at a distance much larger away, we have this screen. Okay? The distance from the screen back to the slits is going to be R. And we know that R is going to be very large compared to D. And D is going to be the distance between my slits here. So that little distance right here between those 2 slits, that's D. Okay. You can see that R is very, very large compared to D. And I'm going to have to kind of blow up this part of the picture here in a minute so we can see what happens. So we know there's a central bright spot directly across, so right there, where they travel an equal distance. But we also know that there's going to be the next bright spot, something like this. That next bright spot occurs when they are exactly one wavelength difference in their paths. So, let me see how I did on. So there's the P0, but here's our next bright spot. And we've got one beam of light traveling like this, and we've got another beam of light traveling like that. In fact, this screen is so far away, it's almost as if those are parallel rays of light. Okay? If that makes any sense? All right. I want to kind of blow up a little part of that picture. What we find is, if we think of there being an angle this makes, let's see if I can draw it the way it is in my notes. And you may want to read through this in your text as well. They do a good job of explaining and probably a better drawing some of this. Blow up where those two slits are so that's a little bit bigger. Okay. We have two beams of light coming through here, about like this. They are almost parallel because they are that this distance is so far back here. But we know that this one travels a little bit longer to reach this bottom, wherever they eventually meet down here to make this first bright spot way far away. But this one has to travel a little bit longer. Okay? If I draw a right triangle here, I can think of, draw this perfectly straight, this making an angle theta. So that's R2. With being directly across. What's the angle it makes compared to being directly across? Okay, that's the angle that we're interested in. This would be theta here also. Okay. How far below, or what angle does it make with being directly horizontal? Well, if I look at this as a right triangle here, my right triangle will say that this angle also would be theta, and this would be a wavelength long. It travels exactly one wavelength. That gives me a relationship that says sine theta, well, sine is opposite over hypotenuse, would be lambda over d. So that first bright spot occurs when we have this relationship, or d sine theta equal lambda. What we're going to find is that other relationships can occur at any multiple. So basically I have that R2, whoops, not R squared, R2 minus R1 has to equal, we already said it has to equal a multiple of this, but that is going to be d sine theta or m lambda. kind of summarize that up, if we want constructive two-slit interference, d sine theta has to equal m lambda. Now, that also has to equal R2 minus R1. So this first part, R2 minus R1 equal M lambda, that's what we found in section 26.1. This d sine theta equals M lambda, that's what we found in section 26.2. I'm going to kind of erase all of this. I'm going to rewrite it. In fact, let's clear this up a little bit. So we get constructive when R2 minus R1 or d sine theta, that's that difference, is equal to M lambda. We know M is equal to an integer, 0 plus or minus 1 plus or minus 2, etc. Or we get destructive interference when they arrive, and instead of being off by a whole number of wavelengths, they're off by an integer plus 1/2 of a wavelength. And again, m equals 0 plus or minus 1 plus or minus 2. Now, when we look at this picture, one of the things that you might realize, I'm going to go back here for just a minute. Here's our slits. Here's our screen. If I draw that straight line across, here's Y0. That's that center point. Here's that first bright spot that's not on this 0. Okay. This angle, this is going to be so close together that this looks much more like this. It looks as if this is coming virtually from the same spot. We know that sine theta would equal y over r. In this case, if I replace that in my formula, I can get a formula that says y sub n over r times d, I'm replacing sine theta, equals m lambda, or ym, it's supposed to be an m, equals, make sure I get this right, r m lambda over d. That's the formula for the location from the center for the bright spots. So again, so if we want to look at constructive interference, all we're using is some basic trig that says sine of this angle is this distance right here, opposite over this hypotenuse, which is approximately r. Technically, this is a tangent, but for small angles, tangent theta is approximately equal to sine theta. I don't know if you know that. But for very small angles, tangent theta and sine theta are approximately equal. So let's write down what we get. Then our results give us what we call Young's formulas from his experiment, and they tell us that for constructive, that distance from the center for the first, and this can be 1 or 2, whichever bright spot you're looking for, is equal to r m lambda over d. D is the distance between the slits. It's not the size of the slit opening, it's the spacing between them. And there again, if we want destructive, we want to know where those dark spots are. M plus 1/2 times a wavelength over D. So we've got really 4 really nice formulas. In a way, these would give us 2 formulas each. We use this d sine theta equal m lambda a lot, but we also use r2 minus r1 equal m lambda. Okay, so those are the formulas that will help you find both the location of the bright spots, or if you want to find the angles, we can find angles. So let's look at some examples that use those formulas. These examples are probably in your textbook. Tell you which one they are. The first one we're going to look at, I believe, is example 26.1. Determining the wavelength of a laser. Make sure these numbers are great. They do. All right. All right, so example 26.1 out of your book. We have a 2-slit setup. D, which is the distance between the 2 slits, is 0.200 millimeters. So we've got 3 significant digits. Those are really close together. The radius of our setup, not the radius, but the distance between the slits and the screen is 1 meter. You'll notice that is very large compared to 0.2 millimeters. And they tell us that the third bright fringe is 9.49 millimeters from Y0, which is the center spot. Okay? So that's the given information. And the first thing they want to know, part A, is what is the wavelength of the laser we used? Okay. Well, if we use that last formula that we came up with, it said that Ym is equal to Rm lambda over D. Okay. So if we are looking for lambda, lambda is going to be Ym times D over Rm. So in this case, the one we know how far the third spot is from the center. I'm hoping everybody understands exactly what I'm saying. It's saying that if your slits are over here and you look at the screen, you're going to have the center bright spot, that's P0, and there'll be 1, 2, 3. You're telling us where this bright spot is, how far that is. That's Y3. How far is that third bright spot above or below? It really doesn't matter. The one above and the one below are the same distance from the center. Okay. So we have all the information we need to solve for the wavelength, so we're going to do that. The wavelength is going to equal, well, 9.49 millimeters. I'm going to need to change that to meters. Ym times the distance. Well, the distance was 0.2 millimeters. So again, I'm going to need to change that to meters. Divided by R is just 1, and divided by M, and M is 3. This is the third bright spot. So I put all of that in the calculator, and it comes out to be about 6.33 times 10 to the negative 7 meters. Another way we might write that is 633 nanometers. That makes sense because I know that visible light is between 400 and 700 nanometers. So if I don't get an answer in this range, and it's supposed to be a visible light experiment, I know I must have done something wrong. That's probably a red light source. 633 is going to look red. It's very close to that 700. Okay, there is part B. So I'm going to leave all of this set up, and I'm going to write down the fact that we now know Lambda is 633 nanometers, because I think we need to use that in the next spot. Part B says, how far apart would the slits need to be so the fourth minimum that's the dark band, is at 9.49 millimeters. So if I can change that spacing between the slits, if I change this value of D, that's the one we're talking about, we're going to change that, I can move things so that I get a minimum at 9.49 instead of that maximum at 9.49. Okay, so our formula for destructive says that Ym equals Rm plus a half lambda over D. And this time we're actually solving for D. We want to know what that new slit spacing would have to be. So D would equal Rm plus a half lambda over Ym. Now we need to think about the value for M. It says the fourth minimum, but the first minimum occurs when M is 0, when they're exactly 1/2 wavelength apart. So the first minimum is for M equals 0, the second one is for M equal 1, then M equal 2, then M equal 3. So the fourth minimum actually is M equal 3. So I want to know G, the distance to the screen is still 1. This will be 3.5 or 3.5 times the wavelength, 633 times 10 to the negative 9, it's nanometers, and 9.49 millimeters, so 9.49 times 10 to the negative 3. Okay. So if I type all that in, R, 3 plus a half, wavelength, location of the dark spot, or the minimum, I get that D equals 0.000233 or 0.233 millimeters. Again, that's a reasonable answer because our original spacing was 0.2 millimeters. I pulled them just a little bit further apart. That changes things slightly, and I see now I get a minimum at that location that used to be a maximum. Okay. The other example we want to do out of this section is example 26.2. Hopefully you can pause this if you need to write anything down. So example 26.2. Talks about a broadcast pattern of a radio station. Now this particular radio station has a broadcast frequency of 1500 kilohertz. It has 2 identical antennas, and they're located 400 meters apart and oscillating in phase. That's important. It says at what distance is greater than 400 meters? No, I'm sorry, let me rephrase it. It says at distances that are much, much larger than 400 meters. So if we are far apart from the screen, in what direction is the signal going to be greatest? So if we're looking at something directional, we're probably looking at something that has to do with angles. This doesn't necessarily seem like a twin slit problem at first, but that's exactly what it is. Instead of having two light sources, we've got two broadcast sources that are 400 meters apart. Put this up a little higher. They tell us that those two broadcast antennas are completely in phase. So we know that if we are far, far away, let's get over here so that we are far, far away. It says, in what direction will the signal, is the signal going to be the greatest? Well, the first thing we have to realize is we don't have a wavelength, but we do have a frequency. If I know for radio wave, that's an electromagnetic radiation, I know it follows the rule that V equals lambda F or C equals lambda F. So the wavelength is going to be C divided by F. Kilo means 1,000, so 1,500 times 10 to the third hertz. And what we find out is our wavelength here is exactly 200 meters. Okay. We're going to need that piece of information, so I'm going to write it right here. Wavelength is 200 meters. If we use our formula for finding direction, we get a formula that says d sine theta equals m lambda. Those are going to be the places where we get constructive interference. Okay, the first direction is actually going to be at 0. We get a maximum with m equal, let's solve this, sine theta equals m lambda over d. But if I plug in m equals 0, I get that theta equals 0. That makes sense. If you're over here at a direction that we're going to call 0 degrees directly across, we expect that right here, those waves would be reaching you in phase, and you would hear a maximum. Okay? What if m equal 1? Well, now we're going to have to do a little more math. So sine theta equals 1. The wavelength is 200 meters. The distance between the antennas are 400, so it's actually just going to be that theta is the sine inverse of 1/2. So when m is equal to plus or minus 1, what we get is the sine inverse of plus or minus 1/2, and that comes out to be plus or minus 30 degrees. So if you happen to be listening at these points that are 30 degrees, you also are going to get a maximum signal. Okay? Finally, the other place it has to happen, we'll do one more. If we say m is equal to plus or minus 2, well, if I put 2 here, I get sine theta is equal to 1. The sine inverse of 1, of course, would be theta is equal to plus or minus 90 degrees. In this case, plus or minus 90 degrees, since this is 0, would be up here somewhere or down here. Now, those are the right answers, but do remember they're only really valid if you are far away. It's not going to be valid if you're standing up in here somewhere. But if you're far away, much farther than 400 meters, those are going to be the directions where you get a peak signal. Obviously, they're reflected on the opposite side too over there. Okay. there is the second part of that question says, okay, well, if these are the directions for maximum intensity, what are the directions for minimum intensity? That's really easy because all I have to do is keep the same formula and change that m to m plus a half. M plus a half times the wavelength over d. Well, the wavelength is still 200 meters, and d is still 400 meters. If I plug in m equals 0, that's where we begin. That's going to be our first minimum half. That's going to be sine inverse of 1/4. That comes out to be plus or minus 14.5 degrees. If I plug in m equal 1, that's going to be sine theta equals 3/4. The sine inverse of 3/4 gives me theta equals plus or minus 48.6 degrees. If I try to do another one, I get a number greater than 1. I can't do a sine inverse greater than 1. So you've reached the point where it doesn't make any sense anymore. Okay? And that makes sense too if we think about the number of maximums we have. We had exactly three maximums. We had a maximum in this direction, we had a maximum at 30 degrees, and we had a maximum at 90. It makes sense that we would have a minimum somewhere in between here. There's that 14.5 degrees, and then another one at roughly 49 degrees. So we have minimums located in between the directions for the maximums. Okay, so that's a good example there. All right, that concludes section 26.2 about two-source interference of light. I will see you in the next video.